everybody! I hope everyone's having a wonderful day. So, last day I had introduced you to the idea of an ordered dictionary. So remember, in an ordered dictionary, each of the records has a key and some data or value, just like a regular dictionary, but it also has this property where each of the records can be compared against each other by their keys so that I can list them from smallest to largest. Or largest to smallest. They have to be comparable. So that being said, I'm going to describe one way you can implement an ordered dictionary. This is maybe the first thing you might try, is try to use a sorted array. So the sorted array contains the records where it's sorted by key. So let's talk a little bit about how you can implement this. So let's talk about the three main ones, and I'll let you think about the rest, okay? So for get, how would you implement get? So we're not going to look for an overly descriptive way of doing it. Just think about the general idea. Now, what would you do? You know the array is sorted, and you're looking for a particular key. So what would you generally do? Well, how efficiently can you do this? You can do this, of course, in login time. How? Just modify a little bit binary search, right? If you don't find the record, instead of returning -1, you'd return back null, right? So you can easily modify get. We can get in login. How about put? How long should put take? So think about what algorithm would be suitable here. Well, what you could do is you could just do it in linear time. So just put it into the spot. That makes it sorted. So this, just to keep things, I'll put this in quotation marks. Put it into the spot that makes it sorted. So, like we've described previously, just put the element into the appropriate spot so that the array maintains its sorted property. Likewise, because it's an array, you may have to potentially resize it, and if that case happens, well, you're going to have to resize the whole thing. It's going to take linear time. Okay? So, in the worst case, we're going to have to shift n-1 elements or increase the length. So, how about remove? How long would it take me to remove an element from this sorted array? Now, the first thing you might try and think is, okay, well, the array is already sorted, so how long will that take me? What it is that you're removing the element with a given key, which means it's going to be anywhere within that sorted array, which would require me doing basically this again, where I find the spot where it belongs, which I can do, which of course I can always search for it using binary search. However, I'm going to still have to shuffle over the potential number of elements. I have to potentially shuffle a whole bunch over, which is going to take me linear time. Because obviously you can't just use binary search and then ignore a bunch of positions, right? There's no gaps you're allowed to have. At least in the way that we've been using binary search. So you see that this is pretty good. I mean, you get logarithmic search times, then you have linear time for those two operations. I'll let you think about the other ones. They're really not too terribly tough. Okay. So this is good for effectively a not too terribly big ordered dictionary. So what's the first thing you might think of doing? Now, on the whole theme of talking about trees, what do you think we're going to try using? We're going to try using a tree. So, what kind of tree are we going to use? The structure that we want to maintain is a proper binary tree. So this is going to be somewhat similar to when we talked about heaps, but it's not really. It's not quite the same. So, we're going to be talking about a binary tree where every node has exactly 2 children. So that means that the children of the internal node have 2 children, and each one is called the left child, one's the right child. So for example, I have a rooted tree here, where I have the root being D, and its left child is A, and its right child is F. Likewise, the left child of F is E, and the right child of F is J. Does E have any children? No, only the internal nodes have children. These technically, in this representation, they don't have children. They don't have a left child and a right child, okay? So, where are we going to go with this? So this is just a proper binary tree. So the key thing that makes it proper is that it has exactly 2 children for each internal node. So remember, we're talking about the internal nodes here. So let's talk about some properties that proper binary trees have. So I've listed out some here. Now some of these are going to look very familiar to you when we talked about heaps. Some of these were actually observations we used for a good chunk of those proofs that we did, or the analyses we did. But some of these are going to be fresh for you, okay? So the great thing about proper binary trees is that the number of leaves is always going to be equal to the number of internal nodes plus 1. That's a nice one to know. The number of leaves is always going to be less than or equal to 2 to the power. See, I'm getting really excited here. 2 to the power, like graphs and trees, they really excite me. 2 to the power of the height of the tree. So the number of leaves is always, it's always bounded from above by 2 to the power of the height. So it's less than or equal to 2 to the power of the height. Really nice. Now the number of nodes at a given level I, so we used this property actually the other day, is that it's at most 2 to the power of I. Then lastly, this is one that you should keep in mind, and this one will be one we will use at some point later down the line. It'll be a fun little property I'll pull out of my hat. Is that the log base 2 of the number of leaves in the tree is always less than or equal to the height, but it's also less than or equal to the number of internal nodes. So this part in particular is rather neat about proper binary trees. So I've drawn out a tree here just to illustrate the third property. So notice that at level 0, we have 1 node. Level 1, we have 2 nodes, then 4, then 8. Okay? So those are some properties of proper binary trees. So some of these are going to really pop up in some of the ways we're going to do things. So where are we going to go from here? Well, the structure we're going to be interested in studying are what are called binary search trees. Now, you may have seen binary search trees in the past, and I'm going to define binary search trees in a particular way, okay? So let's talk about binary search trees. The binary search trees. So a binary search tree, which I'll abbreviate as BST, is a proper binary tree storing records in its internal nodes such that a comma makes it fun, such that each internal node U satisfies what I'm going to refer to as the binary search tree property, the BST property. Which is the following. That every key in the left subtree of U is smaller than, I'll just write it as key of U So it's just the key of U. And that every key in the right subtree of U is larger than key of U. So just to draw you a picture of what I mean by this. So if I have some node, this is U. So that's its key. If I consider its left subtree and its right subtree, and I'm going to often try to draw them with triangles below them to represent their respective nodes below them, because I don't know what the structure looks like below it, okay? So suppose that the node that roots its left child is K1, and the right child's subtree is K2. So if I look at this, the property here would dictate that anything in this left subtree, so any one of these nodes, its key has to be less than K. And anything in this right subtree, any one of the nodes here with the key, all of them have keys by the way, have to be greater than K. Okay? So that's what the binary search tree property says. So I give you some proper binary tree, and each one stores records at its internal nodes. That's a very important thing I need to point out in our definition. So this is what a binary search tree is, at least as far as we're concerned here. Let's talk a little bit about how you implement a binary search tree. So there's a couple ways that you could have talked about binary search trees in the past in a previous course, which is just as valid, but it's not going to jive with this definition quite exactly. This one's a very pure definition that I've given on the right-hand side because it gives us a lot of nice properties to prove some more complicated things. But you'll find that you basically can get away with the first way of doing it. It's very common too. So there's a couple of different ways you can implement a binary search tree. I want to acknowledge these because I like to show you different ways of approaching these things. So there's one way you may have seen in a previous course, which is cool, but I should point this out. So I'm just going to draw the same proper binary tree I had before just to illustrate this. So you may have created a linked structure in the past where D would be indicated as the root, and then each one of these would have as attributes a left and a right child. So this would be left, and this would be right. And you might possibly have a parent reference for each one of the nodes. But the point is that in this implementation, every one of the nodes will have a left and a right attribute, and the leaves will have it where they refer to null, and that's how you can dictate if it's a leaf. So in this implementation, I should point out that these are technically leaf nodes in this representation, and they do store records. Do you see how this doesn't quite match up with the definition or convention I've selected here? So there's pros and cons to this one. So technically anything you can do with this, you can do with this. But I'm going to show you how another way of implementing one. So I'll draw the same one out, the same proper binary tree. F, E, and J. Now, in the convention that we're going to select for this course, what we're going to do is we're going to, instead of having these null references for the left and right, what's going to happen is we're going to have dummy leaf nodes. So all these boxes I've drawn, each of these is a node, but they store no data in them. So what do I mean by this? So if I were to kind of blow up one of these guys here, what it should have in it should look like this. It should have, it'll have a parent reference. Actually, parent, I believe I have it on top. Yes, I do. Let's switch this around. So this will have the element, or your data, or your value, whatever that might be. So this would be your record right here. So the record would be right here. Then you would have a parent reference. Then you would have a left and a right. So this would be typical what you would expect in that implementation. But what makes this one a little different is that these dummy leafs will have null references in all of them except for the parent reference. So the parent reference would point to its parent like this. So note, the only thing that makes this different is that I'm just going to have these leaf nodes here. These are not going to store records. These do not store records. So this left one, you can see that there's different pros and cons to each one. So the pro on this representation or implementation of the binary search tree. So notice that this definition, you can adapt it to make it work with this just fine. It's very easy. You notice that I just don't use these leaf nodes. And so these are basically pretending to be those right there, these dummy leaf nodes. So you treat these as the internal nodes in our definition, which is fine. Just you'd have to be more careful here. So the pro here is that this will use less space. You'll notice that I don't require having nodes at each one of these. I just have to have a null reference. All right? So the pro of this way is that it uses less space, but the con is it makes things a little bit more difficult. A little difficult for implementing some more tree algorithms. So that's mainly the con of it. So if you know how to transfer from this one to that one, you can lose some of the space. But for my purposes, I'm just going to keep with this one, and this will be the convention we're going to use. The pro of this one, you can naturally think, is that it just makes things a little easier. Makes implementation easier. And the con obviously here is that it uses more space. But it's worth stressing that regardless of which of these two representations you use, the asymptotics are exactly the same. So if I give you an algorithm for this one, it's not too hard to transfer between this one to that one and vice versa with some tweaks. But I find very often with some of the more advanced tree data structures, the tree algorithms we're going to be doing, this representation is nice because these dummy nodes operate like anchors where we can perform operations much easier without ever having to really deal with null references. In that implementation over there, you're going to have fun with null pointer exceptions in your implementations. This one, it's a little safer. It's kind of like, the best way I can describe it is it's kind of like working with trees with training wheels. But it oftentimes is very intuitive for some of the more advanced tree algorithms we're going to be looking at in this course, okay? So, just to say, in this course, we're going to adopt this implementation where each one of the nodes, each one of these is actually, it looks like this, where you have a parent reference, has an element or record. So this is a record in here. So this would be a reference to your record object. Then you would have the left and the right. So it's not very much different. The only difference is I'm just going to, instead of having leaf nodes that have records in them, which we're going to interpret in this one as internal nodes where you pretend these dummy nodes just don't exist. Here, you'll just see that it's not really going to be much different. The only difference is that you need to remember that the leaf nodes don't store any records in them. Because let me just give you one more thing that's a contrast. So when you create an empty tree here, your reference to the root, in this one, you would assign it to be null on initialization probably. In this one, the root would be initialized as is an empty leaf node when empty. So it means that when you have an empty one of these, it just looks like one of those. That's it. So when you create the empty tree here, you'll just create a dummy leaf node. In contrast to that one where you create the root being null. So I just wanted to explain these differences, but we're going to be adopting in this course this convention. So where all the leaf nodes, they have dummy values in them. So that means that they're just going to have no data inside of them, except for just the attributes you describe to a node. So it means this one here will just have null, 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 and we just have a care reference, okay? It's not really that special. I just really wanted to spend a little bit of time comparing and contrasting these for you. So when you think about in practice, if you're going between these two, which one might be more ideal? If you don't care as much about space, you can actually sacrifice, and remember, this is just an extra level in the tree, so it's really not that expensive to do this. In contrast here, if you really need to be tight on space, maybe consider trying to refine the algorithm so they work for this one. But in this course, we're sticking with this one. It's quite natural and very simple to work with. Okay? So hopefully that's clear. Just take a look in the notes. You'll see that I give a more complete picture of what one of these trees would look like with these nodes like this. Okay? So just take a look in the notes for that. One last thing involving implementation that I want to talk about. I'm getting excited. Oh, there's the eraser. It's over there. So the big thing I want you to take away from this is that you've seen one way of implementing a binary search tree. I'm showing you a different way in this course so that you have a broad stroke of saying, hey, look, I know how to implement a couple different ways of doing a binary tree. In fact, if you want to technically, you can also count a third way if you count the array-based way I showed you with heaps. The key is I want to show you another way of doing it because there's many different ways of approaching these types of representations. If you've seen this one, this is one prominent way of implementing a binary search tree. This is the other way. So you'll now know all the standard ways that typically people will represent these types of trees, or at least the more common ones. Okay? So I want to make some remarks about how you would deal with this, because the way we're interpreting the binary search trees is that they have unique keys in them. So I'm going to just say ordered dictionaries do not support duplicate keys. However, BSDs are easy to modify. So what do I mean by this? So sometimes in certain applications, you might actually want to have a tree where it isn't like a dictionary where you have the keys being unique. So each of the records doesn't have a unique key. So when you pick, say, something like this or that, you sometimes want to be able to implement something that actually supports duplicate keys. So how can you do that? Well, I'll give you two possible ways of doing this. Now keep in mind that there are ways of modifying most of the algorithms I'm going to show you so that they do support nodes which have duplicate keys in them. Some of the more standard ones do. However, some it'll be a lot trickier to do. And so I'm just going to give you a couple of ways to do this. So if the keys matter, but the data does not. So this means that if you have a whole bunch of nodes and you want to put another node in, but the key is only what matters. The data doesn't. They're just duplicates, right? I just don't really care what that this data doesn't get erased or something. As long as I just have one that maintains that data. So I just don't really care about this as much. If I don't care about that much, I'll just say just use a counter. Just use a counter variable. So in each one of your nodes, what you do is you just keep track of a counter, and whenever you remove a node, you wouldn't entirely delete the node if it doesn't have a counter that's set to 0. But when you put things in, if you get a duplicate, instead of reporting an error, you would increment the counter variable, okay? So if the keys matter but the data doesn't, you can just use a counter, because the data doesn't matter, right? I just care about that, I just have that key occurring again. So if both key and data matter, give each node a collection, which could be a list, depending on your application. So a lot of the time, when it comes to algorithms, if you encounter a duplicate, it really just doesn't matter. You can just pick any one of the ones to return, so it doesn't really make a big difference of how it's stored. The key thing is you just want to give only one element of it. You don't want to go through the entire collection, unless your application demands that. That way you would have to actually be careful of what you choose to be your collection. Okay? So here you can just have each node have some sort of collection with it, and each time you encounter the duplicate, you'd store it in that collection. So, like I mentioned, it's worth noting that you can modify many of the algorithms I'm going to show you. Not necessarily all of them are going to be very nice to do that with. You would have to look up alternate ways of implementing them beyond the ones I show you here. Okay? So, I just wanted to mention that. So there are ways you can handle duplicate keys in a binary search tree. And the big thing I want you to take away from this is that there's more than one standard way of implementing a binary search tree. We're going to select this other approach because you've already seen how you can implement it using this one standard approach. I'll show you this other way where we're going to have leaf nodes that are not going to store any records. The only nodes that are going to store records are the internal nodes, okay? So, that's really all I have to say about implementing binary search trees. Because you've probably seen most of this. The only difference here is just these leaf nodes. That's it. So the first thing I want to talk about are some algorithms for binary search trees. The first one you probably have seen before is called an Inorder traversal. So what is that? It just visits all the nodes, in particular the keys, in increasing order. I can say increasing here because the keys are all distinct. So just as an example, if I draw a tree that looks like this, so I have my binary search tree. Then we'll have 11, 16, and then I think I'm going to have a right child 3. Okay, so here's my binary search tree. So one thing that's worth noting and why we're using this approach is that this ensures that it's always going to be a proper binary tree. That's really, I make it very explicit in how the nodes are structured. So how would you perform an Inorder traversal on this binary search tree? Now remember, I'm just going to visit the ones that have keys in them, right? So all I have to do is do the following. Now remember, I showed you what a pre-order and a post-order are. What do we do in a pre-order? I visit all my, do I visit all of them first or do I visit myself first? In a pre-order, I visit myself first, then I consider all my children, right? Hence the word pre. In an Inorder traversal, I would visit my left child first, then I visit myself, and then I visit my right child. So how would I do this? So I would, before I visit myself, which this is the root, right? I visit my left, and hence I visit my left, and then, hey look, that's a leaf, so I don't count it. Okay, so that means that I need to put down 2. Now I consider myself, I go to my right. Now, don't consider myself yet, I gotta consider my left. There's nothing there. I consider myself. 3, I have a right child. There's nothing there, so I don't do anything. I go back up. Okay, now I have to go back up, and now I consider myself. Right has nothing. Go back up to the root. Okay, I consider myself. And now to the right. Okay, well before I visit myself, I consider all my left child. Nothing there, so I print 11. Okay, I go up. Because I have no right child, right? So I put in 13. I consider my right, which is 16. And then I have no children anymore. There. And I've visited all the nodes. I go back up to the root and say, hey, look, I'm done. Right? So it's not very much different from pre-order or post-order. The only thing is now I have an explicit left and a right. So now I can say visit the left first, then I visit myself, and then I can visit my right. Okay? So this is an in-order traversal. This is a nice property of binary search trees that you can use an in-order traversal. That's the big thing here, is that because we have an ordered tree, we can perform these types of traversals. Because I have a dictated left child and a right child. Does everybody see that? So the binary search tree property guarantees that if ever I look at my left subtree, all the ones that are on my left are all going to have keys that are less than mine, right? So if I root it here, you can say the same exact thing for this subtree. And you can also say the same thing for this subtree, right? You can almost look at them, and this is literally true, is that I can consider these recursive trees such that if I put 10 as its parent, I can merge these two trees. So each one of these is a tree in itself. Likewise, when I merge the two, it's also a tree. Does everybody see that? It's kind of neat. So let's talk about some operations we can do on the binary search tree. So the first operation we're going to talk about is smallest. Now remember, we're trying to implement the operations that I gave for an ordered dictionary. So one of them was smallest. Now, I want you to look at this picture I have over here. Where is the smallest key in my binary search tree? Where is it? Where is it? Come on, guys, where is it? I'm looking at you. Where is it? It is, where is it? Is it here? No. That's the largest one, right? Where's the smallest one? Is it there? No, it's right here, right? 2's right there. But where is that? Notice that if I go all the way down the left by the definition, by my binary search tree property, you'll notice that the smallest key is actually just being stored in the leftmost internal node. Do you see that? So the smallest is always in the leftmost internal node. So we're going to use that idea. The smallest key is in the leftmost, it's supposed to be the leftmost internal node. So, to compute smallest, all I have to do is just find that node. Now, what I'm going to do, I'm just going to make a small modification to my ADT. This is just because, now keep in mind, you can easily turn this into a method that the ADT would accept. But because I'm going to be stacking different methods on top of this one, I'm going to make it return the node itself as opposed to the record. Hopefully this is understandable and very trivial to modify so that you can actually make it return the record. That's the smallest one. Or, sorry, it's value. It's value. So let me write down the algorithm. So I have smallest. Now, smallest is going to take a root node going to take root r of a binary search tree. Now, I particularly use the word root in the same way I use root over here, where I said, okay, well, you can think of this as the root of this subtree, just like that could be technically the root of that subtree. Where all we're going to do is when you give this out, you use this algorithm, you provide it the actual root of the tree, okay? But you should be able, I'll ask you to think about how you can easily modify this smallest method so that you can use it to actually compute the smallest of the ordered dictionary, okay? So I'll let you think about it, but as I said, I'm making small modifications so I can stack different methods on top of each other. You're going to see that once I have smallest, I can solve a whole bunch of the other problems. That's the big thing I want you to take away here. So I'm going to return the node storing the smallest key, or null if the tree has no data in it. So you're going to just return null if there's nothing in it right now. Like there's just that one dummy leaf now that's just sitting there in the root. Okay. So how does this work? I'm just going to go if. So if. Let's make it lowercase I. If R is a leaf. What do we do when we encounter a leaf? What are we going to return when we have a leaf? What do I do when I encounter a leaf? Does the leaf have anything in it? No, right? It does not. So that means I better return null. So remember, whenever you see leaf in this context, we're talking about one of these guys here. Otherwise, we have the following. I'm going to assign a variable. I'm going to assign it to be the root r, so that I'm going to use p to go through this tree and scroll all the way down to the left. Okay? So while p is an internal node, we're going to do the following. So what am I going to do? Well, I have an internal node. So what I want to do is I want to go left while I have an internal node, right? If this is an internal node, I know that I have two children, right? But it might be possible that the child might be a leaf, right? So we don't want to go too far. So we want to make sure we don't go too far. So we want to keep going left until it's no longer an internal node, right? So every time I do this, well, I know for certain it's an internal node, I'm going to go left, okay? So I'm going to P is the left child of P. So I just get the left child. However, there's something wrong with this, at least from my intuition here. Do I want to return P? Do I want to return it? If I execute this loop, if I start it at the root, what happens? I'll go left, 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 and then I get here. Should I return P? No. I don't want to return P. What do I want to return? The parent of P, which I have access to. So I'm going to return the parent of P. And voila. So that's what smallest is for us. And you'll notice that I could just run this on any one given node, because technically, if you look at any one of these nodes, you can just look at it as a subtree, which is in fact a tree. So everybody see that? So So we're going to do the analysis here. Let's do the analysis. We don't want to get yet. I don't want to spoil this. So let's consider the time complexity of smallest. So let's number the lines here. 1, 2, 3, 4, and 5. So I have 5 lines. Which ones are the ones that take constant time? The lines 1, 2, and 5 all take some constant C1 operations. How long does line 4 take on its own? Just constant time, right? To get the left child, it takes constant time. Okay, so however, what's 4 in? It's in a while loop, right? So we have to determine what's going on with that. So the number of iterations of the while loop is at most what? Okay, so I start off at the root and I go left, right? However, how many times do I potentially have to execute this line here? Well, I do it once. I go all the way down the left, right? How many times do I do that? Well, it depends on the number of internal nodes along that left side, but what else? It's at most the following. The number of nodes in the leftmost branch, but how big is that? Which is no more than the height. So if I give you the height of the tree, how big is the height? Well, it can be no more than the height of the tree plus the one node which you started at, right? So that's where I get the plus 1 from. Either way, it's a nice bound on this. Thus, the time complexity is C1 plus C2 times the height plus 1. But what is that? What is that? Well, that's a constant, but this thing is the height. So this is big O of height. So notice in the worst case, it's going to take big O of the height. If you want to get really loosey-goosey, you can technically say it's big O of n, but we're going with big O of the height. Because big O of the height is tighter. Okay, we have enough time to talk about one more operation. Let's talk about get. So imagine I have the same tree I had before, and I wanted to get the record with key 11. So what would I do? I can use the binary search tree property, right? If I know I have a given node, and I look at my left and my right, I know everyone on the left subtree has to have key less than mine. However, all the ones on the right have key greater than my key. So what do I have to do? So if I have a number here that's bigger than 10, where do I go? I go right. 13. Is 13 bigger than 11 or is it less than 11? Well, we know that that 11 is less than 13. So what you do is you use these comparisons to determine if you go right or left, but if you get a match, you return that. However, what we're going to do in this, similar to my previous algorithm that I had, I'm going to kind of tweak a little bit with our ADT. So you can implement those proper ADT methods again. However, with a small modification to what I'm doing here. So all I'm going to do is I'm going to return the node itself as opposed to its value. Okay? What happens if I don't find it? Where do I go? So imagine if I tried getting 12. What would happen? It would not stop here. Instead, it would go down to one of its leaf nodes, and it would return the leaf node itself. So that's when we know we don't have a match, right? So, very simple. It's going to follow a very similar structure. So this is the pseudocode for get. So I give you some root R and the key, and I'm going to return the node storing key K. And if I encounter a leaf, I'm just going to return that leaf node itself. So that's where it should have been stored, should it have existed. So 12 would have been right here if it existed, but it doesn't. So remember, I have this case here where I check if it's a leaf. If it's a leaf, I know right away I'm at a leaf node, so I'm just going to return that. Otherwise, I check if I have a match. If I have a match between the key and the key of R, then I go to return R, because I have a match, I found it. Otherwise, I go left or I go right. So if I go left, then I'm going to return the recursive call of get, where I give it the left child of R, and I pass it the key K as a second parameter. So all I'm doing is I'm just replacing R with the left child of R. Or I go right. It seems really straightforward, so it's actually kind of nice. You might naturally ask, what's the time complexity of get? You'd probably be able to guess it without me really needing to say a whole lot. But I'll do so anyways. What's a worst case scenario here? A worst case scenario is when, that's supposed to be when there, when K, so when key K is not in the binary search tree. So what happens? So what do I do when I have a recursive algorithm like this? What do? I ignore the recursion, then I count up the total amount of work that's being done. When I ignore the recursion, I treat each of those recursive calls as a constant amount of work. Then I incorporate how many times it's going to happen. So ignoring the recursion. All steps together. Take a constant C1 time. How many recursive calls can possibly happen? How far can I go down? Believe it or not, it's the same bound we had before. It's the height plus 1. The number of recursive calls is at most height plus 1. So the total number of operations is C1 times the height 3 plus 1, which is what? It's big O of the height. So another algorithm where it's going to take big O of the height. Did everybody see that? So that's get. So getting things in a binary search is really easy. So when we come back, we're going to talk about some more algorithms for implementing our ordered dictionary with our small little tweaks, of course. So We'll come right back to that next day. So have yourself a beautiful day.